Hello, my name is Geraint Jewell. I'm a Professor of Electrical Engineering at the University of Sheffield and Director of the Future Electrical Machines Manufacturing Hub. This is a 7-year programme of research funded by the UK Engineering and Physical Sciences Research Council, brings together 6 research groups from 4 universities to study many aspects of electrical machine manufacture.
So here at the FEMM Hub, one of the research challenges that we're interested in is how we can understand the manufacturing processes that impact both the performance and life cycle of electrical machines. So for example, processes associated with core forming or core winding, where we want to get a good fill factor or thermal properties, as well as increasing the production speed, or in the connections and terminations phase, where we want to ensure each wire is terminated correctly. Over to my left, you can see an example of our early work. This focuses on manual operations within the electric motor manufacturing process, particularly as it focused on deformable materials, cables and wires. This involved manual operators essentially performing an assembly task. We were wanting to investigate whether machine vision could be used to extract information from this task, for example, the position of the wires, the actions of the hands of the operator, and then provide feedback to the operator whether they've done that particular task correctly, or track if any anomalies have occurred, for example, twisting or bending of the wire. Another piece of work, which you can see just at the back there, is around cable routing. So this follows a similar approach where we're looking to employ machine vision and machine learning models to extract essentially the DLO, in this case the cable, from a particular seam. This is particularly useful in understanding how the operators perform the task, whether they've done it correctly, and the steps they've done it in. To the left of that is a more electric motor manufacturing example. So this is around cable assembly, around the connections and terminations phase, something my colleague Divya has been working on.
My name is Divya Tiwari and I'm a researcher in the FEMM Hub. My research focuses on in-process monitoring and inspection for the process of making terminations in electrical machines. Recent industry survey revealed that the process of making terminations is a highly error-prone manual operation and is difficult to automate. Currently, the defects accrued during the process are detected at the end of line tests. However, detecting a defect at these tests could lead to significant wastage of time and resources. So the solution to this problem lies in in-process monitoring and inspection for both the product and the process by using the latest advances in digital technologies and the well-established frameworks from other domains in manufacturing. Here in the lab, we have developed a thermal crimping system instrumented with various sensors. Thermal crimping is a novel technology that combines the process steps of stripping and joining and therefore allows several benefits such as high takt times and cost efficiency. However, this process is also prone to several types of errors. To understand the correlation between various machine and process parameters and the final product quality, we have used vision-based systems to capture the visible defects such as any burnt insulation in the wires, and we have also used infrared based cameras to capture any hidden defects that are not visible by using vision systems.
Hello, my name is Ioan Alexandru Herdea and I'm a PhD student in the FEMM Hub. I'm entering my final year of the PhD project where I investigate the formation and identification of manufacturing defects of hot crimping with state-of-the-art technology. Because hot crimping is predominantly manual, the research data is very limited and my research aims to fill in this gap with accurate data acquisition and defect identification through automated technologies. As part of the FEMM Hub, I was introduced to the latest technology in electrical machines and digital technologies, which helped me to perform my PhD and connected me with renowned industrial partners.
Finally, what we have done is we've built this particular camera rig. So this camera rig is centered around 3 cameras, essentially built to try and capture 3D data. So not only just the depth data itself from the Microsoft Azure Connect, but trying to use 3 triangulated cameras to essentially build a 3D model of both the human and the workpiece as they perform the particular activity. So the camera rig allows us to capture 3D data. One of the advantages of this is that we can use this 3D information to build a digital twin, both of the human operator as he's performing the particular actions and the workpiece itself. This is a linear core winder that we have sensorized using both vibration sensors and a number of machine vision sensors. The goal is essentially to extract information during the core winding process and then understand and build models around the information that we've extracted to get a better idea of what effect it has on the quality of the coil as it's being wound. So once we've extracted information or the features from this particular set of sensors, we wish to use it in a useful way. In this case, building a digital twin of the core winding process and the coil itself. Think of it as a representation of the coil as it is being wound. This allows us to understand what the effects certain parameters have on the core winding process and the performance at the end, and the coil structure and geometrical faults that may occur. So tied to this work is also our interest in something called an event camera, which you can see up here on the right. This is a biologically inspired camera which works at high speed and allows us to capture the high-speed processes that occur within coil winding. We're also interested in edge compute. So how can we shrink some of the machine learning, machine vision models that we've developed, but onto more industrial platforms, for example, such as the Siemens ecosystem or other industrial grade edge compute devices.